It's I'm very familiar with this project, but it's graphene advanced applications for sustainability, and it's really it goes as to acknowledge LOLC, one of the largest companies, multinational company, but it's but also there's some components that just not Melbourne University, but RMIT also be working together on in different aspects of this the graphene application. So I could even call it like a collaborative project between the two universities working with LOLC. So Thusitha, happy for me to continue, or you want to take over? And then give it about 7 minutes.
Can you? Yeah. So hi, my name is Thusitha, and my project is Graphene Advanced Application for Sustainability. So graphene, I will give you a brief introduction. On the top left corner, you can see here is the molecular structure of graphene. So it is actually a very thin sheet, one carbon atom thin. So you can see here the hexagonal lattice of graphene. So some people call this honeycomb lattice. So if you take graphene like that, graphene oxide is several layers of graphene being stacked on top of each other. So if graphene you call a honeycomb lattice, you can call graphene oxide a honeycomb stack, where honeycomb stack is filled with honey, graphene oxide will be filled with water. So here what you can see is the graphene oxide sheet. So these red dots that you see here, these are the water molecules. So why this water is so important? I'm not the first person who's trying to put nanomaterials in concrete, especially carbon nanomaterials, carbon nanotubes, carbon nanofibers. They've been researched for so long, but the major issue with that is dispersing it in concrete because we can't disperse it in water. But when we have these water molecules, we can easily disperse it in water. Thereby, we can easily, quite efficiently disperse in concrete. So why are we putting this in concrete? Because we are looking for a superhero in concrete. So I'm sure you guys are familiar how Spider-Man tries to shoot his web shooters and try to keep everything together. So what graphene oxide does in concrete, it can attract these water molecules and oxygen functional groups in it to the cement crystals in concrete, thereby keeping everything together. So on this side, what you can see are the findings that we have gotten from our work. So on the top, you can see how the crack path avoids wherever the graphene sheets are. So this is a very new finding. We still have not published it yet. And the second one, I couldn't resist myself from putting it here. So you can see how this is the graphene oxide sheet, and you can see how it's opened up like a stack of cards. These thin sheets, these are the graphene sheets. All together, we call it the graphene oxide. And here, I wanted to put this here because concrete is inertly porous. So graphene oxide not only keeps everything together, it can use its water molecules for internal hydration. When concrete gets harder, it gets thirsty for water. So graphene oxide can give out its internal water when it gets hardened. So that is my research. So this is what we are working on. Thank you very much.
Thank you very much. As usual, an excellent presentation. But I think the finding you mentioned about the last one is totally your ideas, you are thinking. No one has done it. You may get the Nobel Prize for that. No, Manchester got it. Sorry, you already got it. So yeah, sure. I just anyway, there are capable, not only like there are people who presented today may one day go into to Nobel Prizes and all that. All the projects presented today, they are very high quality, which really can be extended into that level. So actually, I'm thinking at high level, which is, I'm not honest comment, not really to exaggerate certain things. So anyway, any online questions? Not yet. So from the audience, any questions from the audience? Yes, Vivian, I'll give you this.
Very nice presentation. My question to you is, what would be the most challenging items for the Superman to get hold of the concrete and then to achieving the expected outcomes that you want as well? What would be the most difficult challenge to use these particular products?
Because actually the expected outcomes, I'll tell you, when we use this in concrete, graphene oxide, what we are trying to do is we are trying to reduce the amount of cement used in concrete. So our results show that we can use 30% less cement and thereby achieve 30% less embodied carbon of concrete. So we are working on it. The biggest challenge is actually the same issue with water, because this nanomaterial attracts a lot of water to it, and therefore the workability of concrete is reduced. So these days, day in, day out, what we are trying to do, we are trying to resolve this workability issue when we use graphene oxide in concrete, because if we can resolve that, then it will be a really good application for the industry, because if the workability is reduced, obviously it's going to demand more PCE, and it's going to demand, or it's going to have a lot of issues when we apply in the field applications. So that is I think is the biggest challenge in this. And also the cost. I think previously the graphene oxide cost was very high. So we are working on reducing the cost, improving the synthesis methods and all of that.
Thank you very much. I think there's, yeah, don't go because there looks like online question.
How about the associated costs?
Associated cost, okay, so the synthesis process, the cost of graphite is not that much. Graphite can be cheaper, but the chemicals that we use in it, we use sulfuric acid and potassium permanganate. So that is quite costly. And the yield, if you talk about from 1 kilogram of graphite, you can make 2 kilograms of graphene oxide. So the yield is so good, but the cost of chemicals is the one that's troubling us. So there are different ways to make this. Chemically, we can make graphene oxide, or electrochemically, we can make graphene oxide. So people are exploring it. So those costs are associated with making graphene oxide.
So thank you, Thusitha. So I think the idea is that why this company is supporting TREMS, so we acknowledge them.
Yeah.
But what they have done is to bring the cost by 1/10 of the normal cost of the geo through the process as well.
To start off, it was around 450, 500 kilograms, 500 USD per kilogram.
4,000s. I bought graphene oxide for 4,000s that time. Yeah, so
The company started with that price, and now they have reduced it even.
that's a company, but 4,000s before. So yeah, so it's very good.
So it's really good.
But it's a good question on the cost, which really brings that. But I also want to say, Studio mentioned that in Japan recently, actually, in fact, TREMS got a very good comments after your presentation in Tohoku recently. Both of us were there last week, I think. Yes, yeah. So the waste, the converting waste into graphite work, which is done in RMIT, some of the plastics to done in another CRCP project that actually, so I think you're planning to use some of the Australian graphites too.
Yeah, we are trying to, because Australia has a lot of graphite, but we have not explored it in Australia yet. And certain other countries like China, Canada, they also have a lot of graphite. So, and I mean, like those of clay graphite, and Sri Lanka, we have weight graphite. So these are different types of crystalline structures in the carbon, atoms in the graphite. So we are exploring all of these things. And one other thing, I think we shared the other day, using wastewater to make hydrogen and graphite. So that is a new thing that we are thinking of, maybe.
Maybe we had David and Asha here, the Southeast water, maybe.
So we saw some articles of that as well, very exciting. So we are looking forward to that.
Yeah, sure. Thank you very much. Excellent presentation. Thank you. Thank you, Alice. Yeah.